So we finished with the first key question, which is on the Earth, structure of the Earth, and that. And we're going to be going on to now natural hazards. We're going to be looking at earthquakes and key question 2, sections 1 and 2. So 221 and 222, natural hazards, earthquakes. All right. So we all know about earthquakes. We've seen earthquakes and maybe even been a part of some earthquakes, depending on where you've lived in your life. And so we all have seen the devastating impacts earthquakes can have. We're going to be looking at earthquakes in 2 sections. This section where we actually talk about what they are, how they work, and the next section about the impacts of them and how they differ in more economically developed countries and less economically developed countries in looking at case studies. So what causes earthquakes? Just basically what we've been studying, plate tectonics. Plate tectonic movement is, I mean, there are other ways earthquakes are caused, but plate tectonic movements are probably are the single biggest cause of big earthquakes, right? So drilling and fracking from natural gas, they can cause minor earthquakes, but most of them are from plate tectonic movement. Really is kind of easy when you think about it. If the plates move vertically or horizontally across each other, there's going to be slippage, there's going to be friction loss, and there's going to be shock waves sent out through the earth. When those waves reach the surface, the energy leaves by massive amounts of shaking and it causes destruction. You're probably most familiar with the San Andreas Fault in California, which is a transform boundary with 2 plates sliding across each other. The other types of plate movement are divergence and subduction, and they can cause earthquakes as well. In fact, the subduction zones are probably the strongest earthquakes. So I'm going to grab a pencil real quick, an old pencil, right? And so what we've got is got this old pencil. And if you guys have one at home, it's a good demo to do. Just kind of feel what we're talking about here, right? So if you've got some kind of wave movement in terms of the slippage, in terms of something breaking, you're going to be able to feel it. So if you bend a pencil more and more and more, and finally it snaps, I could feel that coming through my fingers. Those waves, that movement reverberated through my fingers. And that's what we're talking about here when we're talking about the waves of the earthquake and the energy moving out from wherever that slippage occurred. So I felt a kind of shock or vibration. So that's how it happens. So let's look at the process of earthquakes. We're going to take a look at this diagram, which shows what we call a fault, which is a point of slippage. So if you look right here, this is the fault, which is the crack in the earth, right? So it goes all the way down here, all right? And you can see then it is going this way too, so it kind of be a line that goes down like this, right? So there's your fault in the earth, all right? And it slips, and this one is slipping going this way and this way. It's slipping against each other. Now, wherever there's a hang-up, so where those 2 plates can't just move perfectly, there might be a rock or something that's causing it to hang up. And then at one point, that's what will snap. Where that hang-up is, where that point of movement is called, that is called the focus of an earthquake. That's the point from which all the energy comes out, because that's the point of slippage. And it comes out in all directions, so it'll come out this way, the energy is moving out in all directions, so we basically have these circles coming out here, right? And then eventually it'll reach the surface, and that's where we have issues on land, right? When there is a fault that keeps on having slippage and slippage and slippage, you can get this fault scarp that you can see up here. That's kind of like a ridge that you'd see on land. So the things that we need to know there are, number 1, focus. The focus is the point of slippage in the crust where the waves start. The epicenter is going to be, and I didn't even point that out up here, the epicenter is directly the point on the surface above the focus. It's going to be the point of most damage. And then finally, fault is a fracture in the crust that's been caused by plate movement. The plate movement will then cause slipping along that fault over long periods of time, like the San Andreas Fault in California. Right? And this is the second graphic, and this one describes how waves move. We've got three types of waves in here, and we've already kind of talked about two of them. We've talked about two of them when we talked about how they determine the structure of the Earth. They send P waves and S waves in. Well, the same types of waves are generated by earthquakes. P waves are compression waves, and you can see that in the first diagram here, okay? So the first diagram is the P waves, and they move through. They move very fast, and they don't have much damage. They can travel through any earth material, and they go out from the focus. So these are waves that start from the focus, and they will come first. These will be the first waves that are gone through. They're not usually able to be detected because you really can't feel it. It's moving so fast. It's a compression wave. What happens after that is that the waves, the second type of wave that follows it, is now instead of a compression wave, it's moving up and down in that S pattern, all right, and it's called an S wave. So it moves up and down, causing major damage. It cannot move through the core, so when these ones we send through the Earth, these can't move through the core, and they go out from the focus as well. So these ones emanate at the focus. So these ones cause major damage. Now, if you have a major earthquake with lots of big power, you end up getting surface waves. So these are waves that stay near the surface, and they can also cause major damage, and they go out from the epicenter. So this would be waves that are trapped near the Earth's surface, and they don't actually come out from the focus. They come out from the epicenter, which is on the surface. And you can see that there. So those are three types of waves. All right. So general effects of earthquakes. We've got that two different types of effects we've got in there. We've got primary effects and secondary effects. The first thing that comes to your mind is damage from shaking. So primary effects of earthquakes are going to be buildings falling, bridges collapsing, things like that. So anything that comes from the actual earthquake itself is going to be a primary effect of an earthquake. So landslides, also floods, release of hazardous materials, tsunamis themselves, the actual generation of the tsunami can be a primary effect of an earthquake. All of those can cause major or minor damage depending on severity of the earthquake. But if that isn't bad enough, there are secondary effects of earthquakes. So these are things that happen because these are things that happen not primarily because the earthquake because the earthquake happened, but because something happened that was caused by the earthquake. So these are effects that happen minutes, hours, or days after an earthquake as a result of a primary effect. For example, one of the major types of secondary effect is a fire. An earthquake can lead to a busted natural gas pipe or a gas tank at a gas station, and then if there's any kind of spark, which often happens with an earthquake, that can cause a fire. So that wouldn't be a primary effect, but that would be because the earthquake caused the gas pipe to rupture, then large-scale fires broke out. And then to make matters even worse, another secondary effect could be that a primary effect was that the water pipes were bursted. Secondary effect is you can't put out the fire because the water out, because the water pipes were bursted by the earthquake. And not having available clean water can lead to a secondary effect, which could be disease being spread because you don't have clean water. One of the major damage earthquake events in the U.S. happened in 1906. Maybe you heard about it in history class, but that was more a secondary effect with fires than the primary effect. And I would like you to go to the blog and actually take a look at that earthquake. All right, so foreshocks. Another thing about earthquakes are foreshocks. These are small tremors that happen prior to an earthquake, and aftershocks are smaller tremors following earthquakes. Both can cause damage and surprise people. Some people might think a foreshock was the earthquake, and then the big one comes. Some people may think the earthquake's totally over, and then an aftershock comes. So it's not always time to relax once you've felt an earthquake and gone through it. Where do earthquakes happen? Most of the big earthquakes, 9 or 10, happen along convergent boundaries, so boundaries that come together. Although we do know there are frequent earthquakes at other places like the San Andreas Fault, like we've talked about. This is clearly shown by looking at the figure below. The first shows the plate movement, and the second shows earthquake. So you can definitely see there, while there are a lot around California, you can see A majority of these guys are going where two plates are coming together, if you compare the two. Specifically around here, which is called the Ring of Fire, which we'll talk about now. All right, we'll talk about in the future. So how do we measure earthquakes? As we're going to look at, or maybe by the time you watch this, you've already seen it, in the virtual lab, we measure for earthquake intensity using a seismograph. Seismograph measures seismic shaking, activity of the earth. It's a pretty simple machine. It's got basically a roll tape. It's got a, kind of like what we used in the Earth Model Lab. And then it's got a pen that hangs down and a weight, right? And a base. And basically what happens is that this base will shake with the movement of the earth. And that will cause this pen to record the intensity of those vibrations in the earth or pencil. Right? Now, scientists nowadays don't usually use those anymore. We use like physical ones like that. We have digital ones, much more accurate and quicker. But that's the basic concept behind it. And a very cool thing about seismographs is that they're set up all over the world, and using the data from just 3 of them, we can locate what the epicenter of an earthquake is. And we're going to, of course, explore that in the virtual lab. Why is that important, though? That's important because if we can figure out where 3 of them are on the Earth, we know that their waves emanate from the center, right? So if we can figure out where 3 of them are, we know that where the epicenter is. So the epicenter, or how far from that station the epicenter is. So we know that the epicenter from this station is 3 miles away, right? It can be 3 miles in any direction. But we know from this station, it's 2 miles away. And we know from this station right here, it's 2.5 miles away. All right? This right here where they all meet is probably the epicenter of the earthquake. And so that can let us get aid, relief, and to those areas as quickly as possible. And now with these stations set up all the world and digitally connected, we can find that out in an instant. All right. So earthquakes are given an intensity measurement on something called the Richter scale. The Richter scale goes from 0 to 10, and each integer is 10 times as strong as the previous. So if you're a 2 on the Richter scale, you're 10 times bigger than a 1, but if you're a 3 on the Richter scale, you're 100 times bigger than a 1. So each one goes by 10. The following table shows you how strong the different numbers are and how often they occur. So there's 800,000 that are less than a 3.4 per year. So these are barely even felt, detected only by seismometers. About 30,000 would be noticeable indoors. But don't forget, some of these happen underwater. So not all of these happen on land. 4.3 to 4.8, most people notice them and windows rattle. You get up to the 5.5 to 6.1, only 500 per year. Slight damage to the building, plaster cracks, bridges fall. 6.2 to 6.9, we're starting to get into the damage area. Chimneys falling, houses move on foundations. 15 per year of a 7 to 7.3, that's where you do have serious damage. Bridges twist, walls fracture, buildings may collapse. Only 4 per year of a 7.4 to 7.9. Great damage, most buildings collapse. And at greater than 8.0, only once every 5 to 10 years with total damage. You'll start to see surface waves in these ones, objects thrown in the air. And just for your information, the 2004 Indian Ocean tsunami, or earthquake that caused this major tsunami, was a 9.1 to 9.3 on the scale, the 3rd largest ever recorded. So you're talking even 10 times greater than the one that happens every 5 to 10 years. Earthquakes are devastating, but they have different effects in different parts of the world, and we're going to talk about that in section 2.2.2. And that's it on earthquakes.